Okay, we're going to find another way to find limits. Let's start with the limits on the top, the first six, which we already know how to do. And we're going to talk about another way to come up with it. So some limits you can kind of tell intuitively if you understand the behavior of the graph. So number one here, notice you have a linear function on the top and the bottom is an exponential. And we're trying to figure out what happens in the long run as x goes to infinity. So as x gets bigger and bigger, the exponential on the bottom is going to grow at a much faster rate. So in the long run, you have a fraction. The bottom is getting bigger and bigger. So the whole fraction in the long run is just going to get smaller and smaller. So this limit is really 0. That's what's going to happen in the long run because the bottom of the fraction grows at a much faster rate than the top. And the same thing with number 2, right? You have a number on the bottom, a constant. You have an exponential on the bottom. As x gets bigger, the bottom grows faster and faster. So that limit is just going to go to 0. And number 3, we can do the opposite scenario. On the bottom, you have a quadratic. And on the top, you have an exponential. It doesn't matter what degree of a polynomial you have on the bottom. Even if this was, say, x to the 200th power, in the long run, the exponential function will always grow at a faster rate. So again, we've got a fraction. The top of the fraction is growing bigger and bigger at a much faster rate than the bottom. So this whole fraction is going to get bigger. So really, in the long run, this limit is going to infinity. The last 3 problems down here, we've learned some of these rules before. So remember when we're going towards infinity and you just have polynomials on the top and the bottom, we're going to compare the highest degrees. If the degree is the same, your limit in the long run is just going to be the ratio of these lead coefficients. And this one is 2, 6, which is the same as 1/3. And then let's do number 6 first. Remember we talked about if the degree on the bottom is bigger. Again, the idea the bottom of the fraction gets bigger and bigger at a much quicker rate, so this fraction goes to 0. Okay, this last one here, we're not going towards infinity. So remember, we always do limits problem by a direct substitution. So if I plug in 3, we get 0 on the top, 0 on the bottom, which is an indeterminate form. But we've done this type of problem before. Notice that I can factor the top and the bottom, and these will cancel. So if I plug in 3 now, I get to a limit of 6. So these problems up here are all problems that we've done before. We can either do it algebraically or we've learned some rules for doing it. We're going to learn another way to do all these limit problems, okay? And it's called L'Hopital's rule. And these are going to help us for problems where when you do a direct substitution, you either end up with 0 over 0 or infinity over infinity. Those are called indeterminate forms because we don't really know what that is. So that's when we have to do something else, like on number 5. I ended up with 0 over 0 when I did a direct substitution. So that's why I had to factor it. I'm going to show you another way to do number 5, and this is what L'Hopital's rule says. Instead of doing it by factoring, L'Hopital rule says if you have a limit of 0 over 0 or infinity over infinity, then you can go ahead and take the limit of the derivative of the top function, which in this case is 2x, and divide it by the derivative of the bottom function. The derivative of the bottom is just 1. And now if you take that limit, that will also get you to that same limit. So notice number 5, we could have done it by factoring, or we can use this idea of L'Hopital's rule, okay? The key is making sure that you have 0 over 0 or infinity over infinity before you just start using L'Hopital's rule. So let's take a look at these problems here. So I'm going to check that I have L'Hopital's rule first. And when you're using L'Hopital's rule, you need to check that the top and the bottom are both going to give you 0 or infinity. So if I do just the top, if I plug in 0, cosine of 0 is 1 plus 2 minus 1. That's going to give me 0 here, right? 1 plus 0 minus 1. Sorry, this is 1 plus 0 minus 1. So that's going to give me 0. And then let's go ahead and check the bottom. So if I take the limit as x goes to 0, just the bottom piece, right? If I plug in 0, I do get 0. Now, on a short answer, when you are showing your work for L'Hopital's rule, it is very important that you show that you did the top and the bottom separately. Do not write this is equals 0 over 0 because that's an incorrect statement. 0 over 0 is indeterminate, so we don't want to write that. Okay, so now once we figure out that we are going to use L'Hopital's rule, let's go ahead and apply it. The derivative of the top is going to be negative sine of x plus 2. The derivative of the bottom is 3. And now let's see if I do a direct substitution, do I get to a number? If I plug in 0, sine of 0 is 0, plus 2 is 2, bottom is 3. So this limit is actually 2/3. Okay, let's try this one here. Same thing. So I'm going to check if I can use L'Hopital's rule first. So sine of 0 is 0, so the top will give me 0. And this one, I mean, hopefully I can tell just by looking at it without necessarily writing it out, I will end up with 0 over 0. So L'Hopital rule says I can go ahead and take the derivative of the top, derivative of the bottom, plug in the limit. If I plug in 0, I get 1 on the top, 2 on the bottom. So there's my limit. Let's go up to number 2, same thing. So if I plug in 0 here, e to the 0 is 1, so you end up with 1 plus e to the negative 0 is also 1. 1 plus 1 is 2, 2 minus 2 is 0. So I do get 0 here. And then on the bottom, if I plug in 0 for x, cosine of 0 is 1. So 1 minus 1 is 0. So I do get 0 over 0. So let's do L'Hopital's rule. So derivative of e to the x is e to the x. Derivative of e to the negative x is e to the negative x. But then we need to use the chain rule on that negative x, so it's really a minus right there. And then the bottom, the derivative of negative cosine of 2x is positive sine of 2x. And don't forget the chain rule on that too. Okay. Now, notice what happens here. If I plug in 0 now, oops, this piece is going to be a negative. Let me just rewrite this piece. It's e to the x minus e to the negative x. Notice I end up with 1 minus 1, which is 0. And then notice the bottom, if I plug in 0, sine of 0 is 0. Notice I get 0 over 0 again. So you can do L'Hopital's rule again. So you can do it as many times as you need to get to the correct limit, as long as you have 0 over 0, infinity over infinity. So I'm going to do L'Hopital's rule again. The derivative of e to the x minus e to the negative x will give me e to the x plus e to the negative x. Derivative 2 sine of 2x is going to be cosine of 2x, but then multiply by 2 chain rule, so this is really going to become a 4. And now if I plug in 0, I'll get a 2 on the top and a 4 on the bottom. So 2/4 or the same as 1/2. Okay, we can do the same thing with left hand and right hand limits. So notice I'm approaching pi halves from the left side here. If you plug in pi halves here, the tangent of pi halves, remember, think about your tangent graph. This is your tangent graph. So as I approach pi halves from the left side, notice this graph is going towards infinity. And then secant of pi half, you also have an asymptote there, so that is also going towards infinity. So this one, you end up with infinity over infinity. So I can go ahead and use L'Hopital's rule. Derivative tangent is secant squared. Derivative secant is secant tangent. And especially with the trig ones, before I start plugging in again, let's try to clean this up a little bit. Notice that I can cancel out one of the secants. So I'm going to write this as 4 secant of x over tangent of x. And I'm going to clean this up a little bit more here. Especially with the trig, try to clean it up as much as possible. Secant is 1 over cosine. Tangent is sine over cosine, so when you flip it, one of the cosines will drop out, so really I end up with this. And then if I plug in pi halves, sine of pi halves is 0, so you have 1 divided by 0. But remember, the bottom is not 0, it's approaching 0. So if the bottom of the fraction gets smaller and smaller, the whole entire fraction gets bigger and bigger. Okay, the last thing is you always need to make sure that you can use L'Hopital's rule. I always have people just start using L'Hopital's rule before they check it. So if I look at this problem, if I plug in 0 here, I get e to the 0, which is 1, plus e to the negative 0, which is also 1. So this is 2. And the bottom is 0. So I do not have 0 over 0. I have 2 divided by 0. You cannot use L'Hopital's rule here. Okay? 2 divided by 0 is going to give me infinity because the bottom of the fraction getting smaller and smaller, so the whole fraction gets larger and larger. So make sure when you see fractions, you don't automatically go to using L'Hopital's rule.